7 years ago, humanity witnessed something that should have been impossible. We captured the first photograph of a black hole's shadow, and Stephen Hawking's predictions about what we would see turned out to be terrifyingly accurate. But what you think you're looking at in that famous image isn't what's actually there, and the truth is far more mind-bending than you could imagine. That blurry orange ring that broke the internet in 2019 wasn't just a pretty picture. It was proof that we live in a universe where space and time can be twisted into impossible shapes, where light itself gets trapped in cosmic prisons, and where the very fabric of reality breaks down. Stephen Hawking spent decades explaining why this image would look exactly the way it does, and his explanation reveals secrets about black holes that will change how you see the universe forever. Before we dive into this cosmic mystery, hit that subscribe button because we're about to explore the darkest corners of space-time itself. Look at that image again, that glowing ring surrounding a dark center. Your brain tells you you're seeing a simple donut of hot gas around a black hole, but Stephen Hawking knew better. What you're actually seeing is something far stranger. You're looking at the entire backside of the black hole's event horizon, compressed into a ring around its shadow. You're seeing light that has traveled impossible paths through warped spacetime, and you're witnessing the universe's most extreme physics in action. Here's what Hawking understood that most people miss. That dark center isn't the black hole itself. It's the shadow cast by the black hole's gravity on the light around it. The actual event horizon, the point of no return, sits at the very center of that shadow, but the shadow itself is much larger. Hawking calculated that this shadow would be exactly 2.6 times bigger than the event horizon, and when we measured it, he was right. But why 2.6 times? This isn't random. It's the result of Einstein's general relativity warping space-time around the black hole. Imagine you're shining parallel beams of light toward a black hole. Any beam that hits the event horizon disappears forever, obviously. But here's where it gets weird. Even beams of light that pass well above the event horizon get bent by the black hole's gravity and still end up falling in. Hawking realized that only light rays that pass at exactly 2.6 Schwarzschild radii from the center can escape. These rays get bent just enough to graze what physicists call the photon sphere, a region where light can actually orbit the black hole before escaping to reach our telescopes. Any closer, and the light gets captured. Any farther, and it escapes easily. This creates a sharp boundary, a shadow exactly 2.6 times the size of the event horizon. But the story gets even stranger. That photon sphere at 1.5 Schwarzschild radii is where light can orbit the black hole like a planet orbits a star. If you could somehow stand at that distance, which you can't because you'd be instantly destroyed, you could look forward and see the back of your own head. Light from behind you would curve all the way around the black hole and reach your eyes from the front. Stephen Hawking understood that this photon sphere is what creates the ring of light we see in the image, the bright material in the accretion disk. The swirling matter falling into the black hole emits light that gets trapped in these circular orbits before eventually spiraling away. Some of this light reaches us, creating that glowing ring. Now here's where Hawking's explanation becomes truly mind-bending. When you look at that black hole image, you're not just seeing the front of the accretion disk, you're seeing the entire disk, front and back, all at once. The black hole's gravity bends light so severely that rays from the back of the disk curve up and over the black hole, reaching your eyes from above. Similarly, light from the bottom of the disk curves under the black hole and reaches you from below. This means you're seeing a complete 360-degree view of the accretion disk, compressed into a single image. The light from behind the black hole gets lensed around it, creating what Hawking called gravitational lensing. You're literally seeing around corners in space-time, but it gets even more incredible. Hawking predicted that we would see multiple images of the same regions of the accretion disk. Light can take different paths around the black hole, some going around once, some twice, some 3 times, creating an infinite series of increasingly faint rings. Each ring is a ghost image of the accretion disk, created by light that has taken a longer path around the black hole. The physicist also understood why one side of the ring appears brighter than the other. The matter in the accretion disk is moving at incredible speeds, close to the speed of light. The side moving toward us appears much brighter due to relativistic beaming, while the side moving away appears dimmer. This creates the characteristic asymmetry we see in the image. Hawking's calculations revealed something even more disturbing about what we're seeing. The event horizon itself, the actual point of no return, is completely invisible in the center of that shadow. But here's the terrifying part. We can see the entire surface of the event horizon mapped onto the edge of the shadow. The back hemisphere of the event horizon gets compressed into a thin ring around the shadow's edge. This means when you look at that image, you're seeing every point on the black hole's surface simultaneously. You're seeing the front, the back, the top, the bottom, all compressed into a single view. It's like looking at a sphere and seeing every point on its surface at once, which should be impossible. But black holes make the impossible routine. The image also reveals the black hole's rotation. Sagittarius AI, the black hole at our galaxy's center, spins at incredible speeds, dragging space-time around with it in a phenomenon called frame dragging. This rotation affects how light orbits the black hole, slightly shifting the photon sphere and changing the shadow's appearance. Hawking predicted that we would be able to measure this rotation by studying the shadow's shape and the way light moves around it. The spinning black hole creates a preferred direction for light orbits, making the shadow slightly asymmetric. By measuring this asymmetry, we can determine how fast the black hole spins and in which direction. But perhaps the most profound aspect of Hawking's explanation is what the image tells us about the nature of space and time. The black hole doesn't just bend light, it bends the very fabric of reality. Near the event horizon, time slows down dramatically. If you could watch matter falling into the black hole, you would see it slow down and freeze at the edge, its light redshifting until it fades from view. This time dilation means that the light we see in the image comes from different moments in time. Light from closer to the black hole is more delayed than light from farther away, so we're seeing a composite image spanning different time periods. The black hole is literally showing us the past and present simultaneously. Hawking also realized that the image would change over time as matter moves through the accretion disk. The bright spots and patterns we see are constantly shifting as hot gas spirals inward. By watching these changes, we can study how matter behaves in the most extreme gravitational environment in the universe. The physicist understood that this image represents a triumph of human ingenuity. The Event Horizon Telescope isn't a single instrument, but a network of radio telescopes around the world, working together to create an Earth-sized virtual telescope. This global collaboration achieved the resolution needed to see details smaller than the orbit of Mercury around a black hole 26,000 light-years away. But Hawking knew this was just the beginning. Future observations will show us how the shadow changes as the black hole feeds, how matter spirals inward, and how the extreme physics near the event horizon affects the light we see. We might even detect the gravitational waves produced when objects fall into the black hole. The image also confirms Einstein's theory of general relativity in the most extreme conditions possible. The shadow's size and shape match Einstein's predictions exactly, proving that our understanding of gravity works even in the most warped regions of space-time. Hawking spent his career studying these extreme environments, and the image validates decades of theoretical work. Perhaps most importantly, the image shows us that black holes aren't just cosmic vacuum cleaners destroying everything they touch. They're cosmic laboratories where the universe's most fundamental physics plays out. The matter spiraling into Sagittarius A gets heated to billions of degrees, creating jets of particles that shoot out at nearly the speed of light. These jets can influence star formation across the entire galaxy. Hawking understood that black holes like Sagittarius A are the engines that drive galactic evolution. They regulate how fast stars form, how gas moves through the galaxy, and how the galaxy itself evolves over cosmic time. The image shows us this process in action, revealing the black hole's role as both destroyer and creator. The physicist also knew that studying black hole images would help us understand the information paradox, one of the biggest unsolved problems in physics. When matter falls into a black hole, what happens to the information it contains? The image might hold clues about how black holes process and possibly preserve information. What makes this even more remarkable is that Hawking predicted many of these effects decades before we had the technology to observe them. His theoretical work in the 1970s and 1980s laid the groundwork for understanding exactly what we would see when we finally captured an image of a black hole. He calculated the precise size of the shadow, predicted the effects of gravitational lensing, and explained how the accretion disk would appear distorted by the black hole's gravity. The image also reveals something profound about the nature of information near black holes. Hawking's work on black hole thermodynamics suggested that black holes have temperature and entropy, properties that seemed impossible for objects that absorb everything. The image shows us the mechanism by which black holes can have temperature, the hot accretion disk radiating energy just outside the event horizon. But here's where things get truly mind-bending. Hawking realized that the information that falls into a black hole might not be destroyed but rather encoded on the event horizon itself. This idea, known as the holographic principle, suggests that all the information about the three-dimensional volume of space around a black hole is actually stored on its two-dimensional surface. If this is true, then the image we're seeing might be showing us a cosmic hologram. The light patterns in the accretion disk might carry information about everything that has ever fallen into the black hole, encoded in ways we're only beginning to understand. The image becomes not just a photograph but a cosmic library containing the history of everything the black hole has consumed. Hawking's work also predicted that black holes evaporate through a process now called Hawking radiation. This radiation is incredibly faint for stellar mass black holes, but it represents a fundamental connection between gravity, quantum mechanics, and thermodynamics. The image shows us the environment where this radiation would be produced, at the boundary between the classical world of general relativity and the quantum world of particle physics. The physicist understood that the image would also help us study the innermost stable circular orbit, the closest distance at which matter can orbit a black hole before spiraling inward. This orbit marks the inner edge of the accretion disk, and its location depends on the black hole's spin. By studying how the bright ring in the image relates to this orbit, we can measure the black hole's rotation with incredible precision. What's truly extraordinary is that the image allows us to test Einstein's theory in the most extreme conditions possible. The strong gravitational field near the black hole creates effects that are completely negligible in everyday life, but become dominant near the event horizon. The fact that our observations match Einstein's predictions so precisely is a testament to the power of theoretical physics and mathematical reasoning. Hawking also predicted that we would be able to see the effects of magnetic fields in the accretion disk. The hot, ionized gas around the black hole is threaded with magnetic field lines that can channel matter and energy, creating the jets that shoot out from the black hole's poles. The image shows us these magnetic effects in action, revealing how electromagnetic forces interact with gravity in extreme environments. The image also demonstrates the incredible precision required to observe such distant objects. Sagittarius A is 26,000 light-years away, and its event horizon is only about 12 million miles across. To put this in perspective, it's like trying to photograph a donut on the moon from Earth. The fact that we can see any structure at all is a testament to human ingenuity and technological advancement. But perhaps the most mind-blowing aspect of Hawking's explanation is what the image reveals about the nature of causality itself. Near the event horizon, the normal relationship between cause and effect breaks down. Light cones, which define what events can influence what other events, become so distorted that the future and past seem to merge. The image captures this breakdown of causality, showing us light that has traveled through regions where time itself becomes meaningless. Hawking understood that the accretion disk we see in the image is constantly changing, with matter spiraling inward at different rates depending on its distance from the black hole. The innermost regions complete an orbit in just minutes, while the outer regions take hours or days. This means the image captures motion across vastly different timescales, creating a temporal composite that reveals the black hole's influence across space and time. The physicist also realized that the image would help us understand how black holes grow over cosmic time. Sagittarius A has a mass of about 4 million suns, and it reached this size by consuming gas, dust, and even entire stars over billions of years. The accretion disk we see in the image represents the black hole's current feeding process, showing us how these cosmic monsters continue to grow. What's particularly fascinating is how the image reveals the connection between the microscopic and the cosmic. The light we see is produced by individual electrons spiraling around magnetic field lines, a process that occurs on the smallest scales. Yet this microscopic process creates the glowing ring we observe around an object so massive it warps space-time itself. Hawking appreciated these connections between different scales of physics. The image also shows us something profound about the nature of observation itself. The act of taking this photograph required coordinating telescopes across the entire Earth, synchronizing atomic clocks to nanosecond precision, and processing petabytes of data. In a sense, humanity became a single, planet-sized eye to observe this cosmic phenomenon. Hawking would have marveled at this collective achievement. Looking at that image today, 7 years after it was first captured, we can appreciate the incredible journey that light took to reach our telescopes. Photons emitted by hot gas near the black hole traveled through warped space-time, following impossible curves and loops, before finally reaching Earth after a 26,000-year journey through interstellar space. But the image also raises new questions that Hawking would have loved to explore. How do black holes affect the evolution of galaxies? What happens to information that falls past the event horizon? How do quantum effects modify the classical picture of black holes? These are the questions that will drive the next generation of black hole research. The physicists' work on black hole mechanics revealed that these objects obey laws similar to thermodynamics, with the event horizon area playing the role of entropy. The image provides a window into these thermodynamic processes, showing us how energy and information flow around the black hole. Every photon we detect carries information about the extreme physics occurring near the event horizon. Stephen Hawking never lived to see this image, but his theoretical work made it possible to understand what we were looking at. His calculations predicted exactly what we would see, and his insights help us decode the cosmic message hidden in that glowing ring. The image is a testament to human curiosity and our ability to understand even the most extreme phenomena in the universe. The physicist's legacy lives on in every pixel of that image. His equations describe the curvature of space-time that creates the shadow. His insights explain why the ring appears bright on one side and dim on the other. His theoretical framework allows us to extract information about the black hole's mass, spin, and magnetic field from the light patterns we observe. So the next time you see that famous black hole image, remember that you're not just looking at a pretty picture. You're seeing space and time twisted into impossible shapes, light following paths that shouldn't exist, and the universe's most extreme physics in action. You're seeing proof that we live in a cosmos far stranger and more beautiful than we ever imagined, and you're witnessing the triumph of human reason over the most challenging problems in physics. If this journey through the physics of black hole imaging fascinated you as much as it fascinated Stephen Hawking himself, make sure to smash that like button to support more deep dives into the universe's most mind-bending mysteries. Subscribe to our channel and hit that notification bell so you never miss our latest explorations of cosmic phenomena that challenge everything we think we know about reality. Share this video with anyone who's ever wondered what we're really seeing when we look at a black hole, because these discoveries belong to all of humanity. And let me know in the comments, what aspect of black hole physics amazes you the most? Is it the way they bend light around impossible curves? How they warp time itself? Or perhaps the idea that we might be looking at a cosmic hologram? Drop your thoughts below and join our community of cosmic explorers as we continue to unravel the deepest mysteries of space and time. The universe is full of incredible phenomena waiting to be explored, and with your support, we're just getting started on this incredible cosmic journey together.